Alright, let's do an all-inclusive video discussing circular motion, what it means, where it comes from, and how to interpret any problem that's following circular motion. And this will become important with, first of all, circular motion problems by themselves, but also magnetism problems or electrostatic problems, or even gravitational problems. You can use this to figure out how fast the Earth has to orbit, or if you know how fast the Earth is orbiting, you can use it to figure out the radius. So you can use the velocity to figure out the radius to figure out the velocity, because every radius has an associated velocity with it. You can think about it like those coin machines that you see at Walmart or something like that, where you put the coin in and it spins around and around and around and around. And you can see that the velocity is different based on the radius that it's spinning at. So now that we've at least observed it a little bit, let's get down into the nitty-gritty, the finer details. But to really understand circular motion, it pays to go back all the way to the basics and look at Newton's first law of motion, because that's where all of this comes from. Isaac Newton's first law of motion says an object in motion will remain in motion unless acted upon by an outside unbalanced force. That key word is so incredibly essential, unbalanced. So many people forget that word, and it should never, ever be ignored, because it's the most important word in the entire thing. And similarly, you could say an object at rest will remain at rest unless acted upon by an outside force. Basically, an object's motion, whatever it is, in motion or at rest, object's motion won't change unless unbalanced force is acting on it. And because unbalanced forces cause acceleration, then we can use it more effectively by switching around and saying, oh, if we can observe that an object is accelerating, we know that the forces acting on it aren't balanced. And then we can really start to dissect the problem. So if you ever see a situation, your first thought should be, is it accelerating, or is it maintaining the same state of motion, whether it be at rest or in motion at a set speed? So now let's discuss how to observe whether it's accelerating or not. Again, the three ways that an object can accelerate: number one, speed up; two, slow down; three, change direction. Speed up, slow down, change direction. If an object's speeding up, slowing down, or changing direction, that means it's accelerating. And if it's accelerating, that means the forces are unbalanced. So whenever you look at a situation, you should think, is it speeding up? Is it slowing down? Is it changing direction? If it's not, the forces are balanced. Equilibrium, all is good in the world. If it is speeding up or slowing down or changing direction, that means it is accelerating, meaning the forces are unbalanced. And if you do get into unbalanced forces, if you do find the forces are unbalanced, then your next thought, at least in physics, should be, oh, F equals ma, Newton's second law of motion, actually. So Newton was killing it in this category. Force, the unbalanced force, the net force, the total force, is equal to the mass times the acceleration. Or if we switch the equation around and solve for acceleration, and this is how it appears on the AP Physics equation sheet, acceleration is the unbalanced force divided by mass, or A equals F net over M. Acceleration is the net force divided by the mass. So obviously more force means more acceleration, and more mass, because it's in the denominator, would mean less acceleration. That makes sense. If you kick a more massive object, it's not going to accelerate as much. So we have these three options: speed up, slow down, and change direction. And we're going to break them into two categories. We're going to lump the first two together because they refer to linear motion. Speeding up and slowing down is for an object traveling in a straight line. But changing direction, that's something kind of new, at least from everything we've done up to this point. Changing direction is the other situation. It's no longer linear. Now we're yielding circles, or at least part of a circle. Anytime you turn, even if it's a little bit, if you zoom in on that, you're going to see a small arc that could be turned in to a full circle of radius r. Every turn is part of a circle. And it might be several different turns that are part of different circles, but any turn at all, any change in direction at all, is a circle when you break it down, when you really look at it closely. We will come back to this. We're going to go back to the first two, linear motion, speeding up and slowing down, so we can kind of recap how to use that net force equation to figure out the acceleration. But regardless of whether you're looking at linear or circular motion, the idea is still the same. For any unbalanced force, we have this equation. Net force is mass times acceleration, or acceleration is the net force divided by mass. And that's what I was talking about before. So if we have a 2 kilogram object, and you pull it to the right with 20 newtons of force, and with my big, strong physics teacher muscles, I pull it to the left with 4 newtons of force, well, clearly our forces are no longer balanced, and unbalanced forces cause an acceleration, a change in the object's state of motion, whether it be speeding up or slowing down, because it is linear. Those are our only two options. And we also know the mass is 2 kilograms. Well, if you're looking at the tug of war, you don't care about the individual forces per se, but you do care which force or which direction of force is winning. Well, obviously the force to the right is winning, and it's winning by 16 newtons. So if you want to simplify it, you could say the net force, the unbalanced force, the total force is forces to the right minus forces to the left. And in this case, it's 20 newtons minus 4 newtons. And your net force would be 16 newtons. That's pretty straightforward, right? If you're winning the tug of war, which side is winning and how much are they winning by? So the net force is 16 newtons, but paying careful attention to the direction, 16 newtons to the right. That means the acceleration is also going to be the right, because net force and acceleration, they're that weird old couple that doesn't go anywhere apart from each other. And plugging these into the equation, we can see that we can calculate the acceleration relatively simply. We divide that 16 Newton net force by the mass, 2 kilograms. And when you do that, you're going to find that there's going to be 8 newtons of push for every 1 kilogram that the object has. Or it's going to cause the object to accelerate 8 meters per second every second. So every second, if it's moving forward, it's going to get 8 meters per second faster. If the box was initially moving to the left, it would slow down 8 meters per second. Or rather, it's gaining a positive 8 meters per second. It's gaining 8 meters per second to the right every second.
But I thought you said this video was all about circles.
Chill, Posty. We're getting there. So now we do need to apply it to circles. I agree with you. Everything we've done, though, is still the exact same. Your net force equation is the same. But let's look at it a little bit more closely. Let's look at those forces. If you have an object, let's say an object swinging on a string, going around and around and around, and you're holding it at the center, maybe it's a yo-yo, you're doing it around the world, and we're looking at the forces. If that's the case, object in motion wants to continue in motion, so the object wants to continue straight, but the string pulls it this way, which happens to be pointed directly towards the center. When the yo-yo is here, the object in motion wants to continue straight in a tangential path to the surface. Tangent just means a straight line that perfectly intersects the circle. But the object wants to continue straight, and then it's pulled, wouldn't you know it, right towards the center. Object wants to continue straight, pulled towards the center. That happens on a micro scale. Turn, 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 turn. Even though I have big jigsaws, buzzsaws drawn the whole way around, it happens everywhere. There's always a force pushing towards the center, a center-seeking force. And center-seeking is where the term centripetal comes, where centra, it means center, and petal means heading towards, seeking, going towards. Center-seeking, centripetal. So if a force is always pointing towards the center, it's a center-seeking force. But I want to point out, It's not a force on its own. It's not like a force that you label. It's not the normal force. It's not the force of gravity. It's just like net force. It is the sum of other forces. So that centripetal force, which I'm going to denote as F sub C, is just like when we did net force, was forces to the right minus forces to the left. Your centripetal force is going to be forces towards the center minus forces away from center. So if we look at this yo-yo, if it's in a vertical circle, I see two forces acting on it when it's at this rightmost position. We have gravity obviously pulling it straight down. So we have the force of gravity down. And we have the yo-yo string pulling it directly to the left, where that's your tension force. Now, coming back to this centripetal force equation, it's forces towards the center, well, tensions towards the center, minus forces away from center. There are no forces pointing away from center. That's the other reason I chose this example, is because force of gravity is neither towards the center or away from the center, which means it gets completely ignored from this equation. Only forces towards the center or away from the center will count. So in this case, our centripetal force, our sum of forces towards the center minus forces away from center, is exactly equal to the tension. If that didn't make sense, rewind, rewatch it until it makes sense, because that's crucial. So hopefully now we've figured out the net force in this equation. And I'm going to rewrite this equation where net force equals mass times acceleration. And we're going to rewrite it in terms of center-seeking centripetal, where your centripetal force is equal to the mass times, well, hang on, didn't we say that the net force and mass are always pointed in the same direction? So as you go around in this circle and the net force is always changing its direction, but it's still always pointing towards the center, the acceleration will do the same. That's also changing its direction, it's pointing, but it's always pointing towards the center with that centripetal force. So the way you figure that out, or what we're going to call that, is centripetal acceleration, A sub C. Now at this point, you might want to stick in the tension, but then realize you're stuck, as we still don't have an equation for centripetal acceleration. Well, fortunately, on your equation sheet, that equation is given, where the centripetal acceleration is equal to v squared over r. Much easier, right? So now we can plug this in, and we have v squared over r. So the centripetal force is always going to be equal to mv squared over r. It's not something you have to memorize, as long as you know net force is mass times acceleration, and you have your equation sheet to tell you centripetal force is v squared over r. And that's in the mechanics section of your AP Physics equation sheet. Now the left side of the equation is something you'll always have to derive, because the forces towards the center and the forces away from center are not always the same. Excuse me. So now I want to apply it to one more situation. I am going to apply it to magnetic fields, and we're going to create a situation where we have a magnetic field into the page. And let's assume it's infinite. So it extends north, south, east, and west in all directions. And I'm going to send a proton into this magnetic field. Or rather, a proton is initially moving, and by initially I mean at the beginning of your observation, it's moving to the right. So it has a velocity to the right. And I want to discuss what's going to happen to this particle. Well, your first thought should be, okay, is there going to be an acceleration on this? Is there going to be an unbalanced force? And if you guys haven't done magnetism yet, you're probably going to be lost in this, and it's irrelevant to you. But if you are discussing magnetism, you're probably thinking FBI, right? Or if you're using the right-hand rule, FIB. Both of those rules work. I like to remember that FBI agents always use their left hand. Force, B for magnetic field, I for current or velocity. And those should be written out there for you right now, where force is measured in newtons, magnetic field is measured in Teslas, and the current or velocity, as the case may be, is in meters per second. In this case, it is the velocity of the particle. And let's even give it a velocity of 20 meters per second. And let's give the magnetic field a magnitude of 5 teslas. By the way, I want to point out that velocity for a proton is exceedingly small. But we're going to roll with it because I've already written it down, and I'm fine with that. It doesn't matter. You're just going to get an unrealistic answer, but the process will still be the same. First of all, I want to predict what the particle is going to do before I even consider throwing math into this. So using your FBI, or FIB for you righties, I'm going to consider which way it's going. Well, the magnetic field is into the page, so I'm going to start with my B finger always. So I'm going to point that directly into the page, and then I'm going to pivot my finger until the velocity is pointing to the right, just like it is on this page. And my thumb is pointing where the force will go, which means that there is a force that is pointing directly upward. So eventually that's going to cause the particle to be going upwards. Well, when the particle is going upwards, the magnetic field is still into the page, but the velocity is now up. At that moment in time, the force is to the left. So the particle wants to go straight, but there's a force to the left, and eventually, I think you guys have probably already realized, this particle is going to eventually start moving in a circular path of radius r, because every circle has a radius. So now we have a proton moving in a circle in this infinite magnetic field. And it's moving counterclockwise. I want to point that out. And if we wanted to, we could even figure out the magnetic force, and we could figure out the radius. Wait, how do we figure out the magnetic force? At that point, I'm thinking, okay, we can't use the centripetal force equation because we don't know mass. Oh, we do know mass because it's a proton. We know the velocity, but we don't know the radius. If we don't know the radius, we can't use that equation. But then the equation sheet pops in. The magnetic force equals QVB sine theta. And the only two variables that we haven't discussed in this lesson were Q is the charge, and theta is the angle between the velocity and the magnetic field. Well, if the velocity at the bottom is to the right and the magnetic field is into the page, then your angle is 90 degrees. So your theta is going to be 90 degrees, which means sine of 90 is going to collapse to 1, and we can ignore that. So now you can calculate the magnetic field strength by just plugging in QVB. And I'm just going to very quickly plug that into a calculator and get 1.6 times 10 to the negative 17 newtons. I don't know how that transition went, but we'll see. Okay, so magnetic force is easy to calculate, hopefully at this point, a little bit easier. And if I gave you a follow-up question and said, now wait a minute, what's the radius? At that point, you can use your net force equation. Fc equals mv squared over r. Because it's a proton, the mass is known, that's on your equation sheet. We know the velocity. Radius is still unknown. Oh, but we don't know the centripetal force. However, we do know centripetal force is forces towards the center minus forces away. Well, there's only one force acting on this particle, and that's the magnetic force, which is always pointing towards the center. And again, centripetal force is forces towards the center minus forces away from center. So that should be equal to the magnetic force. So the magnetic force equals mv squared over r, where we know mass, we know velocity, and we know the magnetic force, and with a little bit of algebra, you can solve for the radius. I hope this video was helpful. I hope it wasn't too bogged down, and if you do have questions, please don't hesitate to reach out to me. If you're not on magnetic forces and this last section is completely irrelevant to you, that's okay. The first should really help with centripetal force. And if you have any other questions moving forward, please don't hesitate to reach out to me. And I hope you have a great day. Thanks. Bye.